Namaste, welcome back to Sthita Pragna channel. You are watching machine learning basics theory part. And what are the other parts? If you ask, we have total three parts. One, machine learning projects. Two, obviously one machine learning theory, then projects. Then we also have exam question analysis. So this theory, whatever we are covering here, are the concepts that are asked in the machine learning specialty AWS certification. So that's why we are covering them in depth here. So I am assuming you are here for that purpose. So let's jump into the action without wasting any time. So today's topic is random cut forest. In previous video, we learned about KNN algorithm, correct? And today we are going to learn random cut forest algorithm. What is random cut forest? This is an unsupervised, first of all, this is an unsupervised machine learning algorithm. Remember, KNN was supervised, and this is unsupervised machine learning algorithm, primarily used for anomaly detection. It is used or it is designed to identify unusual data points in a data set, which might indicate anomalies, outliers, or rare events. RCF, we will refer to as random forest going forward, is particularly well suited for detecting anomalies in time series data, but it can also be applied to other types of data. Random or RCF algorithm builds on the concept of random forests, which are ensembles of decision trees. However, instead of using decision trees to classify or regress, random cut forest uses a collection of random cut trees to model the data's normal behavior and identify points that deviate significantly from this norm. How RCF works? RCF constructs multiple random cut trees. Each tree is built by recursively cutting the data space into smaller regions using random splits, also called as cuts. The cuts are made random both in terms of dimension chosen and the position of the cut within that dimension. Data points that lie in smaller, more isolated regions of the trees are considered more anomalous because they represent rare patterns in the data. For example, let's say you have so many points here, but there is only one point here or one point there, correct? So these isolated regions of the trees, so you can consider as this as a big tree, correct? These are considered more anomalous because they represent rare patterns in the data. And then you have anomaly score. Each data point is assigned an anomaly score based on its isolation across all trees in the forest. Okay. Points that are isolated by random cuts in many trees will have higher anomaly scores, right? You have one tree, then you have another tree, then you have another tree. Each tree can represent its own data space. When we come to example, real-time example, you will understand what would a particular tree or data space is considered as. But assume you have this, and that same thing in this tree it is isolated maybe, but here it is not that much, here it is not that much, correct? So these points are isolated by random cuts in many trees will have higher. Obviously, if it is isolated in all trees, it will have higher anomaly score, indicating they are more likely to be anomalous. Conversely, the points that are not easily isolated and thus lie in larger, denser area regions of the trees will have lower anomaly scores, indicating they represent more common patterns in the data. That's the anomaly score. The ensemble method, the forest of trees. Now, obviously, if you have many trees, then you will call it as a forest. These trees provide a robust mechanism for detecting anomalies by averaging the anomaly scores across all trees, reducing the likelihood of false positives or false negatives. Real life example would be monitoring server performance, and an example here would be detecting performance issues in cloud servers. RCF can be applied to metrics such as CPU usage, memory consumption, and network traffic to detect unusual patterns that might indicate a server malfunction or cyber attack. The outcome of this would be proactive identification of server issues, leading to faster resolution and reduced downtime. Another example, sensor data and industrial equipment. What can you use this for? Predictive maintenance in manufacturing plants. This is like the category of that industry, and this is like a specific example in that industry. RCF can analyze sensor data from machinery to identify unusual patterns that might indicate a potential failure. For instance, an expected spike in temperature or vibration levels could be flagged as an anomaly, and the outcome would be predictive maintenance scheduling, reducing the likelihood of equipment failure and improving operational efficiency. A random example here would be in medicine as well. Let's say for a particular cancer, if there are these scenarios, not scenarios but symptoms, correct? So in stage 1 this symptom, stage 2 these symptoms, and when you apply the same models to a new patient who is not even in the late stage, right? Even in initial stage when the symptoms are mapped to these ones, and if they are flagged, then you can clearly know that he might potentially have that particular cancer, but in late stage, so you can identify them. Such kind of, there are so many real-time scenarios you can use these awesome algorithms. Another one is time series anomaly detection, detecting sudden drops or spikes in web traffic. RCF can be applied to time series data representing website visits. Sudden unexplained spikes or drops in traffic can be identified as anomalies, which could indicate a bot attack, server issue, or an unexpected event. Timely response to unusual website activity, improving security and user experience will be the outcome. So these are some examples. Doesn't mean these are all the examples. Now, coming to advantages of using RCF. Of course, scalability. RCF can handle large data sets efficiently, making it suitable for real-time anomaly detection in applications like financial transactions or server monitoring. And it's an unsupervised learning algorithm, which means RCF does not require labeled data. If you remember, the previous one, which was KNN, is a supervised, which needs data that is labeled. Here you don't need to label it, making it ideal for scenarios where anomalies are rare or not well understood in advance, so that you have the labels. And the ensemble of trees helps to reduce false positives and false negatives, providing a reliable method for anomaly detection. And considerations when using RCF. While RCF can detect anomalies, it doesn't inherently explain why a data point is considered an anomaly. Further analysis may be required to understand the root cause. And the effectiveness RCF can depend on the choice of parameters such as the number of trees in the forest and the depth of the trees, etc. So those are some things that you need to keep in mind. Before going to conclusion, our favorite part, what is it? A scenario based example or walkthrough of this particular algorithm. For this scenario, we are going to have a data set of credit card transactions. Each transaction, it will have the following features. What is it? Transaction ID, amount or the transaction amount, time of day, location or the country, and the merchant category. And this is some sample data. Just have a look at it. If you look at this, these are very few transactions, but looking at this, you can figure out transaction 4 is suspicious or might be suspicious due to first high amount, unusual time, and different location, because based on all these transactions you can clearly know that this person lives in USA and he doesn't spend more money more than $1,000, but this one meets all this, so this might be a suspicious transaction. Now let's get into the random cut forest. Okay, so what is the first step? Creating the data space. Remember, we spoke about the data space representing a particular tree. Each transaction can be represented as a point in a multi-dimensional space. So close your eyes, think of space or multi-dimensional space where you have multiple points. We know two-dimensional, which is this one. Three-dimensional, when we look anything, it's three-dimensional, right? Go beyond that, say multi-dimensional, just saying that. Okay, you don't have just x-axis where you have amount, time of day. Instead, think of more dimensions where you have amount, time of day, location, and all those things. Correct? For simplicity, though, we'll just consider a 2D space with transaction amount and the time of day as the axis, right? Transaction amount, you can say time of day, you can put as this axis. The RCF algorithm starts by making random cuts through the space. Now you imagine the space. In the space, you have all these as in a multi-dimensional space or in a 2D. Then now RCF comes and it kinds of makes random cuts through this space. So when you say random cut, what does it mean? It means selecting a random dimension. Okay, so what dimensions we have? We have these. Let's take transaction amount as a dimension. Let's say it went and it made a random cut, and then selecting a random position within that dimension to split the data. What does that mean? Okay, so cut 1, it split the data at a transaction amount of 100 USD. Okay, let's say 50, 100 or something like that, right? It made a random cut at 100 USD. And then you have time of day, let's say 2 a.m., 3 a.m. or p.m., 5 p.m., 6 p.m. Okay, now you made cut 1. Again, as I said, a random cut. It means selecting a random dimension. So since we assumed 2D, we only have 2 dimensions. Let's say we did a random cut at $100 and again a random cut at 6 p.m. This process creates a tree structure called a random cut tree. Now, since you cut this, whatever you made the cut, it will be it will create a tree structure, and that's what you call random cut tree. Why is it called random cut tree? Because the tree was created out of randomly cutting different dimensions. Okay, now so this is all. Let's say you already have it. Now a new transaction is processed, which is what we mentioned in here. Okay, which is 5000 USD. Time of day is 3 a.m. Even though we said location, since we considered 2D, let's only consider these two. This transaction is plotted in the data space and evaluated by the random cut trees. The RCF checks how isolated this particular transaction is. If it quickly becomes isolated by the random cuts, example, if it falls into a small region of the tree that doesn't contain many other points, it indicates that the transaction is an anomaly. Correct? How does it work? Let's see. Now you made a random cut tree. You made, what is it, 100 USD and 6 p.m. If you look at this, this is 3 a.m. Okay, let's assume if this is a plot where this shows all our normal transactions like this. This one is like 3 a.m. and 6 p.m. is too far. It is somewhere. And $100, this is the cut, and 5,000. So by, as you can see in this particular tree, this random cut tree, it will be somewhere else. It is clearly an outlier. Let's say you made another cut instead of 100. Let's say you did another cut at 500 USD and let's say 10 p.m. Even in this, it will be an outlier because amount is 5000, time is AM. So you can imagine, right? Then based on different cuts, the algorithm does those random cuts. In each one of them, this transaction will be an outlier. I hope you are understanding that. And each tree in the forest will give the new transaction an anomaly score based on how isolated it is. And clearly this will be isolated in all of them. If the transaction is isolated in many trees, it will have a highly anomaly score just like this particular one. I hope you are following me. Let's say I'm just giving an example. Instead of 5000 and 3 a.m., let's say 5000 at 8 p.m. If you do that, at least in a dimension where you cut at 8 p.m. or 9 p.m., it won't be isolated, correct? Because 9 p.m., 8 p.m. is the normal ones. Many transactions are happening at that time. At least it won't be. But this one is in both cases or mostly any random cut you do, it will be isolated. Okay. So sample anomaly scores I have right here will look something like this. Okay. So if you see the first transaction, second, third, this, and this is the fourth transaction and this is the new transaction. I mean, you can consider both as the same. It doesn't matter. But if you look at this, highly anomaly score of 0.95, indicating it's very different from the others. Transactions with high anomaly scores are flagged for further investigation. In this case, the new transaction with a score of 0.95 would be flagged as potentially fraudulent. You might be thinking, well, this is all good, but if I see a graph, I will understand more. Well, that's why I have this one right here. So whatever values you have seen so far, as you can see, we considered 2D, but the algorithm considers multidimensional. We cannot imagine all that in our head, but algorithm can. So since we consider these two, by plotting those details, so we got all these points. If you see here, what do we have? X-axis transaction amount and Y-axis time of day. So this shows the data points, which are the transactions, and the random cuts that split the data space. So you can see this is a random cut that happened here, and then this is a random cut that happened here. So time of day, oh sorry, this is amount cut and this is time of day cut. Okay, and these are existing and this is the new transaction. So what can you see from here? The new transaction would be plotted as an outlier because it is far away from your random cuts. Pretty much all these are in the same tree, correct? Not in the same tree, but at least in each cut. In this cut they are together, in this cut they are together, but in both the cuts this is far away. So this is an outlier, indicating this is a fraudulent transaction. Okay, what are the, if you have to summarize, transactions are plotted in a multi-dimensional space, even though we are showing 2D space here. The space is randomly cut into regions. Now you know what a data space means. And anomalous transactions are quickly isolated in the trees. You can see that here. High scores indicate higher chances of fraud, and transactions with higher scores are flagged for review. And this is my first time actually explaining machine learning concepts, so I really want to know how am I doing, like am I making sense or is it too confusing, etc. So please do let me know in the comments, because if you don't give me feedback, I won't know where I am lacking, so that you won't be giving me an opportunity to correct myself. But if you do comment, then that gives me an opportunity to improve myself, correct myself. So let me know how am I doing. Like if you are new to machine learning, are you able to understand based on what I am saying, or you are still not able to? So let me know in the comments. I really like feedback. It doesn't matter whether it is positive or negative, it doesn't matter. I take it. I take all kinds of feedback. So do let me know in the comments. So the conclusion, RCF is an effective and scalable method for detecting anomalies like fraudulent transactions. By analyzing how isolated a transaction is within a forest of random cut trees, RCF can identify outliers without needing labeled data, making it a powerful tool in dynamic environments. So at least at a high level, we know that random cut forest is unsupervised, KNN is supervised. At least that we can answer if somebody asks. Anyways, that being said, that's about for this particular video. I hope you enjoyed, the explanation here. If so, don't forget to subscribe, like, and comment. I really appreciate you spending your time here, and do let me know in the comments and likes as well. Based on that, I will know you people are interested, so that I will get inspiration to make more videos, more such videos. All right, see you in the next video. Have a great day. Peace out and love you all.